So as we mentioned in the last section, our objective is to find a model that not overfits nor underfits to the training data. We want a model that generalizes well. This is a model that is balancing bias and variance. How do we do that? Well, we do it with what's called hyperparameter tuning. Hyperparameters are what we call the knobs to twiddle to control the complexity of a machine learning algorithm. And when we control the complexity, we're controlling the bias variance trade-off. So not all algorithms have hyperparameters. However, as the complexity of our models increase or we get more flexible models, therefore the ability to capture and conform to more complex relationships in our data, we tend to see an increase in the number of hyperparameters. The proper setting of these hyperparameters, unfortunately, is dependent on the data and the problem at hand and isn't always known beforehand. So we need a method of identifying the optimal setting or the optimal values. For example, in this data set that we were looking at in the previous section where we had these individual data points that are, you can see it's nonlinear, non-monotonic, and we're trying to find a model that provides a prediction line that does a good job of conforming to this relationship and would generalize well. Well, if we used a k-nearest neighbor model, k-nearest neighbor models have a single hyperparameter called k, and it determines the predicted value to be based on the k-nearest observations in the training data to the one being predicted. So if k is small, such as k equals 2, we see that in the upper left-hand corner, the model will make a prediction for a given observation based on the average of the response values for the two observations in the training data most similar to the observation being predicted. So this often results in a highly variable predicted values because we are basing the prediction, or in this case, an average, on a very small subset of the training data. But as k gets bigger, we base our predictions on an average of a larger subset of the training data, which naturally reduces the variance in our predicted values. Right? So averaging often helps to reduce variance. So in this image we see here, we can see that we are using a k-nearest neighbor where we have k equals 2, k equals 5, k equals 10, 20, 50, and 150. And we can see that the smaller k values tend to have high variance in their prediction line, right? You can see it's kind of very squiggly and they're chasing individual data points or training data points. But as our k value gets larger, and we're averaging our predicted value, or we're averaging multiple observation response values to be our predicted value, we can see there's this naturally smoothing out of our line. And what's happening is we're reducing the variance and increasing the bias. And we can see that, from k equals 10 to k equals 20, we're getting a much smoother line. K equals 50, somewhere between 20 and 50, it looks like there's this nice smooth line that conforms to the relationship. But then as k gets even larger to k equals 150, we start getting these flat lines here. And that's because our model is becoming overly biased. Okay? So a small k value has too much variance, as we see up here, and a big k value has too much bias. So there's some sweet spot, probably somewhere between k equals 20 and k equals 50, that is the optimal value for k that creates a nice smooth line that conforms to the pattern in our data and that will actually generalize well to unseen data. So how do we find this optimal value? Well, one way is we could actually just fiddle and manually adjust hyperparameter values until we find a great combination of these values that result in high predictive accuracy, or we maximize or optimize the generalization error. However, this can be very tedious and it takes a long time. Not something that we want to do. So an alternative approach is to use what's called a grid search. And a grid search is an automated approach to searching across many combinations of hyperparameter values. In essence, what it does is it predefines a candidate set of values for our hyperparameters. And then we're going to apply a model with each combination of hyperparameter values. We use a resampling approach such as cross-fold or k-fold cross-validation. And we train our model using k-fold cross-validation with these hyperparameter values. And we get our generalization error. We record that. And then we repeat the process. We pick another set of values for our hyperparameters. And we apply our model using cross-validation. We record the generalization error. And then again, we change the hyperparameter values and rinse and repeat. Okay, so for example, with this example that we saw earlier, where we are looking at k equals 2 all the way up to k equals 150, our grid search would actually take values ranging from 2 to 150, and it could be literally values 2, 3, 4, 5, all the way up to 150. Or maybe we want to search just even numbers, 2, 4, 6, 8, 10, and so on up to 150. Or maybe we search, 10, spaced out evenly across 10 different values between 2 and 150. And we're going to apply this model and record the cross-validated generalization error for each of the values for the hyperparameter. And then we can look at which one actually optimizes our results. So in this case, we see that as we go from k equals 2, right here, we have an RMSE, a cross-validated RMSE value of over 1.05. But as we increase k, we see this decrease because we're going from a high variance model and we're adding bias, and it's reducing our variability. And we come down here, we kind of see this trough here, this sweet spot down here where we're minimizing our RMSE. But then as the model gets overly biased up here towards 100, our error goes up again, right? And so that's because our model is becoming too biased and our performance is decreasing again. So we can see that where we optimize our cross-validated RMSE is right down in here. And actually this ends up being k equals about 46, right? So you can see that that's just below 50 here. And we could imagine what that nice smooth line would look like that conforms well to the data, and it's going to generalize quite well.